So last Tuesday, we discussed the joint distribution function of two random variables. So now we will extend the concept to a finite number of random variables. All right, so the first of all is the joint cumulative distribution function what we call the JCDF. X1, X2, Xn of n random variables. X1, X2 up to Xn. Okay, is defined as here. So it is the probability of the joint event of X1. The first random variable is less than X sub 1. The second random variable is less than X sub 2 up to the value of the nth random variable is less than X sub n. Okay. For all variables x1, x2, xn in R. Okay. Okay, and we know that this is the intersection of n events. Okay, so it's the intersection it's the intersection of n events. And so this is then an event in the sigma algebra F, and so it has a probability measure. Okay, so this is the definition of the joint CDF of n random variables. All right, and from the joint CDF of n random variables, now we can compute the marginal joint CDF of a subset of these n random variables. Right? So marginal joint CDF, right, which is x sub I1, x sub I2, x sub I sub k, into x sub I1, into x sub I2, up to little x sub ik of k random variables, x sub I1, x sub I2, up to x sub ik, with k is greater than or equal to 1 and less than or equal to n1, n minus 1. And the indices will be I1 greater than or equal to 1, less than I2, less than ik, and less than or equal to n. Okay. So you can see this is just k random variables out of these n random variables. Okay. And so we call them as the joint CDF because that when k is greater than or equal to 2, then we have joint CDF. but they are marginal. Because why? Because that these k random variables are just select from the n random variables. Okay. So this marginal can be computed. Okay, can be computed from the joint CDF f of x1 of x1, x2 up to xn as follows. Okay, so the f xi1, xi2, xi sub k, i1, xi2, xi sub k. As we know, this is the probability that the x sub i1, let's say equal to little x sub i1, x sub i2, let's say equal to little x sub i2, x sub I sub k, let's say equal to little x I sub k. Okay, and this is equal to p intersection j from 1 to k, x sub I sub k less than equal to little x I sub j. Okay, intersect with I from 1 to n, but I not equal to subtract to I1. Okay, and xi less than infinity. Okay, so, and we know that each of these events is the total event. Okay, this is the total event. Okay, and we compare, so that would be f of x1, okay, at the limit. So, and x sub I goes to infinity for all I in minus I1. Okay. Okay, so that by taking multiple limit, okay, for the argument that x sub I goes to infinity, which for all index I, okay, not in this set. Okay, so this is, so you can see the marginal joint CDF of k out of n random variables can be computed from the joint CDF of n random variables by taking this limit. Any questions? So for example, suppose n equal to 4 in the case. So the f of x1 and the x3, okay, this is the limit. x2 goes to infinity, and x4 goes to infinity of okay, and this is equal to fx1 infinity, x0 infinity. Okay. And fx2, which is just the CDF of the second random value except 2. So this is the limit. x1 goes to infinity, x3 goes to infinity, and x4 goes to infinity of the joint CDF of x1, x2, and x3, and x4. Okay? And so this is f of infinity, x2. Okay. Any questions? Okay, and in principle, any joint probability statement about x1, x2, up to xm, okay, about these n random variables can be answered in terms of their joint CDF. Okay. Okay, so that is very important to have the joint CDF of n random variables. Okay. Now we will see a statement about unrandom variables. Okay. Then before that, we extend two cells in real plane to n cell. So an n cells in the n-dimensional, the real n-dimensional space is the Cartesian product I1 times I2 times up to times n, Cartesian product of n intervals I1, I2 up to In in R. Okay, so an n cell, all right, is just the n tuples such that the ith component is in the ith interval. So this is the n cell. Okay, and so the event that the random vector, which consists of n components, so each one is a real value function on the sample space. All right, so when we put together, so this is the vector valued functions defined on the sample space. Okay, and the vector function has a value in an n cell. All right, so the random vector has value in the n cell. All right, and this is actually an event. It's the event that x1 has value in I1, x2 has value in I2, up to xn has value in In. So this is the intersection of xi in ii. All right, and because each x sub I is a random variable, okay, so this is an event of interest in the sigma algebra F by definition of a random variable. And so intersection of the n events in F give us an event in F too. All right, so that this is in F. All right, so you can describe the joint event this way by comments, or express the same joint event by random vector. Okay, by random vector. This random vector is in this n cell. Okay. Okay, right, and the probability and that such kind of event all right, so the probability of this random vector in this n cell can be computed from the joint CDF of x1, x2, up to xn. Okay. Right, and for example, we have okay, so so the probability that x1, x2, x in okay, in this n cell, and this is actually equal to, so that I1 is this semi-infinite interval, okay, and this is indeed the probability that x1 is less equal to x1, and capital X sub 2 is less than equal to little x sub 2, and the nth random variable has value less than equal to x sub n. So this is exactly the joint CDF of the n-random variables. Okay, so for this special case. And also, if we change the interval a little bit, so for example, we just change I1 to be this one. I turn the closed end to the open end. Okay, and the other, and we do not change the other interval. And as you can see, this is actually equal to so we have x1 less than equal to x1, but x2 less than equal to x2, etc. And this is actually equal to the limit. Okay, and say Tn go up to x1 of probability okay. Oh, T1, sorry. The parameter go up, okay, and okay, by the continuity of the probability function P, okay, and so that this is the limit. T1 go up to x1, and this is f T1 x2 that's the xn. Okay, so that T1 approach to x1 from the left, so that this is equal to f of x1 minus x2 up to xn. Okay. Okay, and here, so here is by the continuity of P. The probability function P. Okay. Okay, and furthermore, if we have but okay, now we change in from this closed interval to the open interval here, and so this is actually equal to f of x1 x2 up to xn minus 1, but xn minus here. Okay, so that this is the left limit. Okay, and so you have, if you continue, so that you have a lot of, if you continue to do so, if you change all the closed end, right end to the open right end, then this is the what becomes to be x1 minus x2 minus 2xn minus. Okay. And for okay, it's in A1, A11, A12. So if we, I1 is the half open, half closed. So the left end is open, but the right end is closed. All right, so this is I1, okay? So that's I1, this left open, right closed, left open, right closed, left open, right closed. If we have that, then it's very interesting that the term, and as we know, if n equal to 2, they are 4 terms. So how about when we have general n, all right? And so this would be okay, the summation of J1, J2 up to Jn is in 1 and 2. Okay. And the minus 1 raised to the power A plus J2 plus Jn, and the f of A1, J1, A2, J2 up to An, Jn. Okay. For all mass infinity, that's then AI1 okay, then equal to AI2 AI2 and less than infinity. Okay. So we have 2 to the nth power terms here. So if n is 10, then we have 124 terms. Okay? So even though we can compute it, right? So this I1 is this type, I2 and In. Right? So that All right, and so all right, and also if it's in A11, A12 plus A21, A22 plus A31. Okay. Now, if the interval, all right, here, each of the I sub I is cross interval, right? So this is a special case for n equal to 3, and we can compute it from so we can have A12, A22, A32 here, minus f of A1. So if we replace 1, 2 to 1, 1, then we should put the minus sign, the left limit, and A22 and A32. Okay? So these two remains the same, but when we replace A122, so this is the right end, okay? Replace to the left end for the first interval, then we have to put the left limit. Okay. Similarly, we have 3 such case. So it's A12, A21 minus A32. Okay. So we replace this by this one, and the minus A12, A22, and A31 minus here. All right. So now we have subtract too much, so we have add back. All right, and we have A back is A. Now we replace. Here we have 3 right ends, right? But from the 3 right end, we select 2 from 3, change them to be the left end, and take the left limit. So this is A11 minus A21 minus and A32 plus f of A11 minus A22 and A31 minus plus f of A12, A21 minus and A31 minus. All right, and then but we add too much, so we will subtract f or the left end. Okay. So the computation of probability of this event such that the random vector has value in an n cell. All right, the random vector has value in an n cell. This probability can be computed from the joint CDF of these n random variables, but may be a little bit complicated. Okay, just as I have illustrated by these examples here. Okay, but in any way, any such probability, okay, can be computed from this one in principle. Okay, anyway, so do you have any questions? All right. So if no questions, then we follow the argument for 2 random variables last Tuesday. Then we will consider 2 special cases. The first case is when x1, x2, when the n random variables are discrete. And take one of the values. Okay, so we say A1, J1, A2, J2, AN, JN. Okay, respectively. Then we define the joint probability mass function called JPMF of x sub 1, x sub 2, up to x sub n. As here, little p of x1, x2, xn. So it's defined to be the probability that okay. So the probability that random variable x, the first random variable has exact value equal to x sub 1, all right, and the capital X sub 2 equal to the little x sub 2, etc. All right, and we know this is equal to the probability that x1 equal to A1 J1. x2 equal to A2 J2 xn equal to A n J sub n. Okay. When xi is equal to A I J sub I. Okay, and will be 0 otherwise. Okay, so we define a real value function. Actually, this is non-negative, right? Non-negative function, all right, on the n-dimensional real Euclidean space. So that, as you can see, the value of the joint PMF is 0 except for n vectors, for vector points, which has components in the possible values. Okay, in the possible values. So this is the joint PMF. All right, and the marginal joint PMF little p xi1 xi2 xik of little xi1 xi2 xik of k random variables x sub i1 xi2 xi sub k with k greater than or equal to 1 but less than or equal to n minus 1 and 1 this equal to I sub 1, less than I sub 2, I sub k, and okay. Now can be computed from the joint PMF P to the px1, x2 up to x sub n of x1, x2 up to xn as follows. Okay, so we can check I1, I2, xi sub k, A, I1, j, I1, A, I2, j, I2, A, ik, j, ik. Okay, so you have to be careful for the indexing. Okay, and this is equal to summation of for j sub I, okay, for all I not equal to I1, I2 up to ik, and sum over all possible A1, J1, 2, J2, AN, Jn. Okay. And little p, x I1, x I2, x ik, x I1, okay, so that's right. So for example, with n equal to 4, little p, x2, x3, and a, 2, j2, a3, j3, okay, would be equal to summation j1, summation j2 of p, little p, A1, J1, A2, J2, A3, J3, A4, J4. Okay? So it's a double sum. And little p, x2, x3, little x2, little x3 is equal to 0. Okay? For all x2, x3 not equal to A2, J2, A3, J3. Okay. Okay. So this is the case that the all random variables are discrete. Any questions? This is the first special case. Now we consider the second special case. N-random variables x1, x2, up to xn are called jointly, absolutely continuous if there is a non-negative and integrable function f of x1, x2, up to xn on Rn, i.e. f of x1 will be greater than or equal to 0 for all points in Rn, and the n-fold integral of the function is finite. Okay, so this is the n-fold integral. Such that for any n cell I1, that cross continuous product I2 times times In in Rn. Okay. The probability that this random vector has value in the given n cell, right, has probability which can be computed from this function. And this is indeed the n-fold the integral of the function f over the n cell. I forgot to And because that each variable is in I1, okay, so this means that x1 is in I1, x2 is in I2, xn is in In. Okay. And indeed, the integration, the unfold integration can be computed in actually. So so I think the unfold can be computed by iterative integration. So here, okay. So you can do the integration over xn. All right, over xn, this is become to a function of x1, x2 up to x sub n minus 1. And then you over x sub n minus 1. All right, so you can do the iterative integration. Okay, so the unfold, the integral can be computed by, and the order will be independent. All right, the order can be, so indeed we can have x sigma 1 in I sigma 1 dx sigma 1 x sigma 2 in I sigma 2 dx sigma 2 x sigma n minus 1 in I sigma n minus 1 dx sigma n minus 1, and finally x sigma n in I sigma n f of x1 dx sigma n, where sigma is a permutation of the index, say. Okay? So it's just a permutation. And both of them is by Fubini's theorem. Okay? Because that this is non-negative. A kernel is negative and integrable. Okay? So we can apply to here. Okay? So the kernel, the integrand, non-negative integrable. All right? And so that the order of iterative integration is independent to the evaluation of this probability. Okay, so it is very nice for that. Okay, so you can see that these events, okay, it just says that the first random variable has value in the first interval. The second random variable has value in the second interval, etc., up to the nth random variable has value in the nth interval, right? So this is a joint event, okay? Because they should occur simultaneously, okay? And so the computation of this probability can be evaluated by the unfold integration, okay, over this n cell, okay? Right? So such a function fx1 in above is called a joint probability density function of x1, x2, up to xn. Okay, so it's JPDF. Okay, so to check whether n-random variables are jointly absolutely continuous, then we have to establish a joint PDF for these n-random variables. Okay? So by definition, you have to check that this identity will be true for any n cells. Okay, for any, this is in principle. Okay, by definition, but an easier way is here. So the remarks. One. That the total event has probability 1, but the total event can be expressed by the statement here that the random vector has value in Rn. Okay? So, and which means that okay, so that this becomes to be okay. So maybe I will write down here. So the unfold integration of the joint probability density function over the Rn should be equal to 1. Okay? So this is a necessary condition we can have. The second thing is that x1 is in I1. xi sub 1 is in I sub 1, but xi is equal to a specific value, and xi plus 1 in I. Right? So this probability, okay, by definition, is that Okay. A to A. Okay. Now, and we look at here this iterative integration. Okay. So this is equal to a g function of x1 I here. Okay? But when we integrate this function over xi, okay, relative to xi, but with the interval from a to a, so this is just a point, okay? So that we can see that this is actually and this is 0, okay, since dxi is 0, okay, this is 0. Now, so the integral becomes to 0, and so this is 0 too. Okay? So this shows that if x1, x2, up to xn are jointly absolutely continuous, okay, each x sub I is a continuous random variable for all I from 1 to n. Okay? So if n random variables are jointly absolutely continuous, means that if this n random variable has a joint PDF, then each of them is a continuous random variable. The third point, to verify that a non-negative and integrable function f of x1, x2 on Rn is a joint PDF of n random variables. Right, to just them, it is sufficient okay, so it is sufficient to check that. We check that the joint CDF of this n random variable. So this is All right? All right, can be evaluated by the n-fold integration of f functions over the n cell. Okay, and by Probability theorem, it can be evaluated iteratively. So that would be dx2 dt1, sorry. dn minus 1, and okay. All right, so the joint CDF can be evaluated by this non-negative integrable function f, okay, in this way. For all okay, to check. So this is a sufficient condition. Of course, it's necessary, all right, by definition. But to check the identity for special types of N cells, okay, will be enough, okay. So that this is our special types of N cells here, okay. So if this is true, then this non-negative and integrable function f is a joint PDF, okay, of the random variables. And because we have find a joint PDF of a random variable, so this random variable must be jointly absolutely continuous. Any questions? All right. Now, as we know, N cells are important in describe events which is related to N random variables. Okay. All right, now, so the smallest, so we will define the Borel sigma algebra in Rn, as we define Borel sigma algebra in R1 and R2. So the smallest sigma algebra, which contains all N cells, I1 times I2 times In in Rn is called the Borel sigma algebra. in Rn. Okay, denoted as squid B sub n. Okay. So how do we establish the Borel sigma adjoint on? Well, you can use the n cells as the basic members in squid B to nth power, and we do the countable complement, intersection, and union. Okay, so that's any member in squid Bn is called a Borel set in Rn. Okay. So we now state a proposition like a proposition 6.1.a. Okay. Unreal value so unreal valued functions x1 from x2 on the sum space are random variables if and only if the vector function has value in C. Now C is any Borel set in Rn. Okay, it's an event of interest in F for any Borel set C in Rn. Okay? And the proof will be omitted. Okay, so you can see that. So this is the event. This is the event which can be described by the unrandom vectors, the unrandom variables x1, x2, up to xn. Okay. Okay, and so we let f of x1 to be the collection of all events described okay, such that C is okay. Oh. Which is the collection of all events in F described by x1, x2, up to xn. Okay. Okay, so we collect all such kind of events, okay, for all C in the script B to N, so that C is all possible Borel sets in Rn, okay. So we collect them together, all right? And then it can be shown. Then it is easy to justify that f of x1, x2 up to xn is a sigma subalgebra of f, okay? And so that it's called the sigma algebra generated by x1, x2 up to xn. Okay? So remember, we have defined the sigma algebra generated by a random variable x before, right? In chapter 4. Okay? Now, if we have a finite number of random variable x1, x2, and xn, then also this random variable can be used to describe events, okay, in this way. And it is actually a sigma subalgebra of the sigma algebra F, okay. And the proof will be similar to the proof we have done in chapter 4 for a single random variable. Okay. Okay. So that the events related to n random value will be in this sigma subalgebra. Okay. All the events which will be discussed in probability theory will be in this sigma subalgebras, which means that it's in this kind of event. Okay, which is described that the random vector has value, okay, in a Borel set in Rn. Okay, and a Borel set in Rn is just a countable complement intersectional unions on n cells. So the very basic Borel set will be n cells, okay, in Rn. Okay, and we use these n cells to do set operations like a complement, union, and sections. But the total number of set operations will be countable. Okay, you can do countable such operations. Okay, such operations here. Now how do we evaluate the probability of such an event? it can be shown that if x1, x2 up to xn are jointly absolute continuous random variables with a joint PDF f of x1, then for any Borel set C in Rn, we have, so we can compute the probability of this event. Okay, the probability of this event okay. Yeah, the probability of events to be the n-fold integration in C okay, so we'll be in here. Any questions? All right, and in last chapter, chapter 5, we talk about data processing on a random variable, right? Now, it's possible to do the data processing on n-random variables. For example, to compare two random variables, right? So the result of the comparison is the data processing of two random variables. Or you will do some ordering of n-random variables. Okay, so this is a data process of n-random variables, right? Okay, and we talk about that if the data processing function is Borel measurable. Okay, so then the result of data processing is again another random variables. All right, so first of all, we define Borel measurable functions in n variable. Okay, and now a real valued function G on an n cell is called Borel measurable. If for any Borel set B in R, the inverse image of B so the image is that okay, so the inverse image of B under G is a Borel set in Rn. Okay, so it's Borel set in Rn. Right? And so we can write down a proposition 6.1.c. If G of x1, x2 is a Borel measurable real value function on an N cell, then the data processing on the n random variable x1, x2, xn by G, okay, is a random variable too. Okay, for any random vector x1, x2, up to xn, whose range so the range is contained in the N cell. Okay. Okay. So by using a Borel measurable real value function, okay, defined on N cell, and we know that the random vector has range in this N cell. Then this data processing, okay, the G on this N random variable again is a random variable. Okay. And the proof is actually similar to what we have done in chapter 5. All right, now since G is Borel measurable, okay, the inverse image of any Borel set in R, okay, is a Borel set in Rn, okay, for any Borel set B in R. Now since x1, x2 up to xn are random variables. Now we look at the event. Okay, so we look at this event. This is a function, right? So this event, as we know, is the same as the random vector has value in the inverse image of B. Okay, so this is the same. All right, and we know this is in, so this is in Bn. Okay, as we say, the inverse image of B is a Borel set in Rn, so this is in the script B to N here. All right, and so that this is in F right? By proposition 6.1 point B. Okay, we just show here, give here. Which says that x1, x2, xn are random variables if and only if that this is an event of interest in F. When C is the n-dimensional Fourier set. Okay, so we know this is an n-dimensional Fourier set, right? Fourier set, and this is random vectors. Okay, so this is an event in F by this proposition, and so that go back here, which shows that this the value is in a Fourier set, all right? It's in F, okay? So that G, x1, x2 up to xn is a random variable, okay? By proposition 5 point, I forgot. Let me check. I think this in chapter 4. I forgot. All right, in chapter 4. Okay, so this proposition. Okay, so if the data processing function is Fourier measurable, then the result is again a random variable. Okay, so the next proposition will describe, all right, very general types of Fourier measurable functions. But before that, we can define a real valued function g x1, x2 to xn on Rn is called piecewise continuous. Okay, so if it is continuous in Rn, or there exists a piecewise smooth hypersurface which partition maybe I extended it. A real value function on an N cell. Is called piecewise continuous if it is continuous in the N cell or there exists a piecewise smooth hypersurface which partitions by removing the hypersurface all right, the N cell into countably many disjoint open sets U sub I in Rn such that G is continuous on each U sub I. Okay, so it's called piecewise continuous. So for example, for n equal to 2, okay, and we look at, so this is I1, this is I2 here. And if we can partition so maybe this is U1. This is U2, U4. Okay. Right. So we have a rectangle here. And the hypersurface consists of all the green boundaries here, right? Some is line segment and some are curves. Okay, and so after removing the hypersurface, then we lift counted many disjoint open sets, U1, U2, U3, U4, and U5. So there are 5 disjoint open sets. And so that the G restrict to UI is continuous on UI. Okay? So it's called piecewise continuous. All right, so it is an extension of piecewise continuous function on an interval, right, in the real line. Okay, this is an extension. Okay. And so we describe a proposition 6.1 point D. Any piecewise continuous real valued function G on an N cell X Borel measurable. Okay? Okay. So piecewise continuous functions give us a very wide, a very big class of data processing function used in many different disciplines, and they are Borel measurable. So we can use piecewise continuous functions on N cells to do the data processing on N random variables. And the result should be a random variable too. Okay? Any questions? Okay, so the first section of chapter 6 describe a number of general random variables. Okay, and in the second section of this chapter, we'll describe special types of N random variables. Okay, we call the independent random variables. Okay, independent random variables is various two types of random variables Okay, a very special kind of relations in a finite number of random variables. Okay, and so again, we define independence among random variables starting from just two random variables. Okay, so two random variables, x and y, are said to be independent if for any interval I and j in R. Okay, so for any, the joint probability, okay, which means that the random variable x has value in the interval I, and the random variable y has value in interval j simultaneously. This joint probability is the product of the probability that random variable x has value in I, and random variable y has value in j. Okay. Okay. So the identity must be true for any intervals I and j. Okay. So this is the definition of independent random variables. Okay. And it can be shown that two random variables, x and y, are independent if and only if for any Borel sets A and B in R, the joint probability that random variable has value in A, random variable y has value in B is equal to this probability times this probability. Okay, so this definition is much more easier to check, right? Because we just need to check for intervals. Okay, and the statement here says that if this is true, then the same identity is true for arbitrary Borel set. Okay, for Borel set. Right. And further good technical proposition to identify whether two random variables are independent okay, if and only if the joint CDF of x and y is equal to a product of the CDF of x and the CDF of y. Okay, And this actually is that is showing that X is in okay, or maybe I talk about so the checking, the proposition says that the checking of this identity will be enough for special types of ing. What special type? Well, when I is this type, the semi-infinite interval with the right cross end. You can see here. Okay, and this probability is exactly the joint CDF. Okay, so it's easy, much more easier, right, to identify whether two random variables are independent. All right, we just consider their joint CDF and their marginal CDFs. So which says that the joint CDF of X and Y is equal to the product of their marginal CDFs. Okay, so that is it's a very good technical proposition to have. Okay, a very good. Okay. All right. So I think I will stop here, and because I covered chapter 6, so my speed a little bit slow. Yes. I'm sorry. Morning. Okay. Good. So so I will give an online lecture, okay, on Saturday, all right? And so you can either to watch the online video or you can see the recorded video, okay? All right, and so I will notice you what is the time for the online video in the morning of the coming Saturday. Okay, so I stop here.